Welcome. In this lecture, we shall discuss the interplay between the microcosm and the macrocosm, the interaction between the world of elementary particles and the dynamics of the universe as a whole. Let us first discuss what we understand about the microcosm. Now you might say, why bother about the world of elementary particles and their interactions? After all, we are interested in the universe as a whole. We are interested in things like the homogeneity of the universe, the flatness of the geometry of the universe, the formation of galaxies, and so on. You will soon see why it is important to understand the interaction between elementary particles and the interplay between the microcosm and the macrocosm. In the previous lecture, we saw that in order to understand the horizon problem, or the homogeneity of the universe, and the flatness problem, the universe must have experienced an early period of exponential expansion. In order for that to happen, in some period, gravity must have acted as a repulsive force, resulting in an acceleration of the universe. This phase is known as inflation. More precisely, inflation is a stage of accelerated expansion of the universe when gravity acted as a repulsive force. Graphically, this is what I mean. Plotted on the y-axis is the scale factor of the universe, or the radius of curvature of space in general relativity, and the x-axis is time. Inflation is a period around 10 to the power minus 35 to 36 seconds when the universe expanded exponentially. And as I'll argue, this was due to the fact that during this phase, gravity acted as a repulsive force. And then this was followed by the usual and familiar Robertson, Friedman, Walker decelerated expansion of the universe. You'll remember that I referred to Alan Guth, elementary particle physicist in MIT in Boston, and he was constructing models for the grand unified phase transition, about which I shall describe presently. But that's what he was attempting to do. And in the process, he discovered a possible model for the exponential expansion of the universe. As I mentioned in the previous lecture, he argued that the grand unified theory phase transition at a time when the universe was 10 to the power minus 35 seconds old could be one of those supercooled first order phase transitions in which the universe was trapped in a metastable state, a thermodynamically metastable state, or as particle physicists would refer to it as a false vacuum. So the universe is trapped in this false vacuum for a while. And the exponential expansion of the universe occurred during this phase. So now we have to understand, what is this grand unified theory? What is this grand unified theory phase transition? And why it has anything to do with the price of fish, as they say. In this case, the exponential expansion of the universe. Let us begin with the four forces of nature. The strong nuclear force between the particles inside the nucleus, the electromagnetic force, the weak nuclear force which mediates radioactivity, and the gravitational force between massive bodies. The important thing for you to appreciate is that the strong nuclear force has a very short range, whereas the gravitational force acts between masses as far away as you like. Now let the strength of the strong nuclear force be 1 in some unit. Then the point to appreciate is that the electromagnetic force is 1,000 times weaker, and the weak interaction force is 10 to the power minus 16 times weaker, and gravitational force is roughly 10 to the power minus 41 times weaker. In other words, if we consider the strong interaction between two protons inside the nucleus and the gravitational force between two protons inside the nucleus, the ratio of those two forces will be 1 is to 10 to the power minus 41. So these are the 4 forces of nature. In our world, they are distinct forces described by distinct theories. The gravitational force is described classically by Einstein's general theory of relativity. So far, there is no quantum theory of gravity. This is, of course, one of the great unsolved problems of physics. The electromagnetic force, the classical theory, is, of course, due to Maxwell. The quantum version of electromagnetic theory is known as quantum electrodynamics, and this explains the forces between charges as arising due to the exchange of virtual photons. These are not real photons, these are virtual photons. Quantum electrodynamics is perhaps the most successful of all of fundamental theories that we know till today. Indeed, it is considered as the jewel of physics. Now, according to quantum electrodynamics, the interaction between two electrons is mediated by the exchange of a virtual photon. And for constructing a successful quantum theory of this interaction, Tomonaga of Japan, Julian Schwinger of Harvard University, and Richard Feynman of Caltech were awarded the Nobel Prize in 1965. This was a very important breakthrough in quantum physics, to construct a quantum theory of electrodynamics. Now let's go to the weak interaction, the forces mediating radioactive decay of, say, the neutron. Enrico Fermi, the great Italian physicist, he was a great theoretical physicist as well as an experimental physicist. In 1934, Enrico Fermi constructed a spectacularly successful theory of weak decay, such as the decay of neutron into proton, an electron, and a neutrino, or today we would call it an antineutrino. And what Fermi said was that a neutron decays to a proton by spontaneously creating an electron and an antineutrino. This was a very revolutionary idea. The electron and the neutrino don't exist inside the nucleus. When a neutron spontaneously decays to a proton, then an electron and an antineutrino are spontaneously created. Just as when an atom jumps from a higher level to a lower level, a photon is spontaneously created. The photon doesn't reside inside the atom. So this theory of Fermi was not only very successful, but it was truly revolutionary. Now let us turn to the strong force between the neutron and the neutron and the proton, and the proton and the proton inside the atomic nucleus. The first attempt to construct a successful theory of what binds the nucleus together or what holds the nucleus together was by Yukawa, a well-known theoretical physicist in Japan, and that is Hideki Yukawa. He explained the force between the nucleons as due to the exchange of a particle which he called as the pi meson. He argued that because the nuclear force is short range, the particle that is being exchanged must be a massive particle. And that massive particle was found in 1947. Let me stress that the electromagnetic force between two electrons has an infinite range. Therefore, the virtual particle that is exchanged, the virtual photon, has to have a zero mass. On the other hand, if the force is short range, then it makes sense to say, based on Heisenberg's uncertainty relation between energy and time, that the virtual particle must be massive. Indeed, Yukawa estimated that its mass must be roughly 700 times the mass of the electron. And this particle was discovered in 1947, and 2 years later, in 1949, Yukawa was awarded the Nobel Prize for Physics for this very important discovery. Then around 1950, the role of symmetry became apparent in formulating the laws underlying the interaction between elementary particles. So let us try to spend a little time understanding where symmetry comes in and how it influences subsequent discoveries. First, let us consider the remarkable symmetry between the neutron and the proton as far as nuclear force is concerned. Yes, the proton has a charge and the neutron is electrically neutral. But as far as the nuclear interaction goes, the force between two neutrons is the same as the force between two protons or the force between a neutron and a proton. This led people to the idea that as far as the nuclear force was concerned, the neutron and the proton, since they behave very similar to one another, must be the same particle except perhaps for an internal quantum number, which they called as the isotopic spin or isospin for short. Remember, a neutron, a proton, electron, they all have intrinsic angular momentum. You don't ask where this angular momentum came from. It exists. And we know that from spectroscopic splitting of lines. In a similar fashion, physicists hypothesize a new internal quantum number called isotopic spin or isospin. So this led to the idea that apart from the electric charge, the neutron and proton were the same particle, except one of them, the isotopic spin, was pointing in that direction with respect to some chosen axis, and for the other particle, the isotopic spin was pointing down with respect to the chosen axis. So it is just like an electron spin being up or down. So the isotopic spin up, let us say, is the neutron. Isotopic spin down, let us say, is the proton. So we have an internal symmetry which was being invoked to understand the similarity between neutron and proton as far as nuclear force was concerned. Now, this line of thinking of internal symmetry and internal transformation of particle between one to another led to several revolutionary ideas. First, it led to the idea of quarks. In the 1960s, Murray Gell-Mann at Caltech and Zweig, his collaborator there, launched the very novel idea that neutron and proton were not fundamental particles. They were, in fact, composite particles made up of three quarks. These quarks have fractional charges. I shall explain in a moment. These quarks obey Fermi-Dirac statistics. So here they are. there are two quarks. One is known as the up quark. Its electric charge is plus 2 by 3 times the charge of the electron. And the down quark, whose electric charge is minus 1/3 of the electric charge of the electron. So if I want to make a proton with an electric charge of plus 1, then all I have to do is to have two up quarks and one down quark. Now if I want to construct, I'm having problems with my antivirus popping up. I beg your pardon. So if you want to construct a neutron, then you have two down quarks and one up quark. That will make it minus 2 by 3 and plus 2 by 3, which will give me an electrically neutral particle. So the proton and the neutron are bound states of three quarks. The quarks are fractionally charged. So this was the idea that emerged in the 1960s. And soon the quarks were discovered in deep inelastic scattering of electrons or protons. Now, what binds the quarks together? After all, if protons and neutrons are bound states of quark, then something must be binding the quarks together. Those particles were called by Gell-Mann as gluons. They glue the quarks together. For the first time, symmetries played a role in advancing this idea that neutron and proton were not fundamental particles. They were in fact composite particles made up of three quarks. Gell-Mann and Zweig were led to this idea based on symmetry considerations. Now the question is, why don't we see free quarks? After all, we used to say the nucleus consists of neutrons and protons. How do we know? Because we see neutrons and protons in free space. Similarly, if quarks are there inside the nucleons, the neutron and the proton, why don't we see quarks? Why don't we see the up quarks and down quarks? Well, that took a while to understand, and then emerged this idea of quark confinement and asymptotic freedom. If you consider two neutrons or two protons and the nuclear force between them, then the nuclear force decreases dramatically as the distance between the two particles increases. Similarly, the electrostatic force between two electrons decreases as 1 over r squared. But the force between quarks increases as the distance between the quark increases. By the same token, the forces between the quarks disappears when the quarks are confined to very, very short distances at very, very high energies. So this is the notion of quark confinement. Quarks are confined to the nucleons because it will cost you an enormous amount of energy to liberate the quarks. Right? And when the quarks are confined inside the nucleon, they behave like free particles, non-interacting particles, as it were. So that is the notion of asymptotic freedom. And for enunciating this principle and elucidating it, three physicists were awarded the Nobel Prize for Physics, three physicists at Princeton University. Now we come to the eightfold way. Now, even when strong interaction between neutron and proton was being understood, in terms of the particles themselves being bound states of three quarks, new particles were being discovered, and the decays of these newly discovered particles were also being studied. First, these new particles were discovered in cosmic ray interaction with matter. Cosmic rays which come from distant galaxies, quasars, black holes, pulsars, neutron stars, and so on. Then, after the Second World War, man-made accelerators were produced. And these accelerators enable people to collide elementary particles against one another at very high energies. And in these collisions, these new particles were produced and their decays were observed. What new particles am I talking about? For just to give you an example, lambda particle, the sigma particle, the cascade particle, and so on. Many, many particles, the enormous zoo of particles. Now, to understand the decay of these particles, a new quantum number called strangeness was invented by Gell-Mann and by Abraham Pius. Now, when I was a student at the Fermi Institute in Chicago a long, long time ago, I was assigned a little desk to sit as a beginning graduate student. There is a room with 5 or 6 desks, one desk for each student. And in my desk, it was written with a ballpoint pen, strangeness was discovered here. So I was very thrilled. That was the table in which Murray Gell-Mann sat when he had this idea of a new quantum number called the strangeness quantum number, and he scribbled it on the table. Now, experiments soon showed that the strangeness quantum number was conserved in strong interactions. Whenever there was a decay of these particles into other particles, strongly interacting particles, this new quantum number strangeness was always conserved. Namely, the total strangeness quantum number on the left-hand side of the reaction was equal to the total strangeness quantum number on the right-hand side of the reaction. So just as charge is conserved, momentum is conserved, energy is conserved, lepton number is conserved, baryon number is conserved, strangeness is also conserved, but only in strong interactions, not in weak interaction. So, when particles like lambda, sigma, cascade, etc. decay, the strangeness quantum number, which was hypothesized by Gell-Mann and Pius, was conserved in these reactions. Now, in the 1960s, Murray Gell-Mann at Caltech and independently Neyman, an Israeli physicist at Caltech, independently were playing a game. The game was to arrange the newly discovered hadrons into geometrical patterns. What geometrical patterns? These geometrical patterns were dictated by group theory, which is a branch of mathematics. It is a method of describing symmetry operations. So let us see. Let us consider a book, and I can do various transformations of the book. I can flip the book this way. I can flip it like this. I can flip it like this. I can flip it like this. This set of operations forms what is known as a group. Mathematicians will tell you that if it satisfies these and these properties, then this set of operation is called a group. Now, this is not the time or place for me to digress into group theory, which is a very beautiful branch of mathematical physics, but I shall merely illustrate it through this diagram. Here, for example, is an octet of particles. The neutron, the proton, sigma minus, sigma 0, sigma plus, and the lambda particle over there. Cascade particle with a minus sign, cascade particle which is neutral. So, the strangeness quantum number of the first row is 0. The neutron and proton strangeness quantum number is 0. The strangeness quantum number of these 4 particles is -1, and the strangeness quantum number of the last 2 particles is -2. So Gell-Mann and Neyman independently were able to arrange these particles into this very satisfactory pattern. Then they try to arrange these other particles into this pattern. lambda minus lambda 0, lambda plus plus, then sigma particle, the cascade particle. Well, it didn't quite fit into a nice triangle. If it had to fit into a nice triangle, there would have to be a particle over here where I'm pointing with my cursor. The strangeness quantum number of that particle must be -3 because this is strangeness 0, strangeness -1, strangeness -2, and so the strangeness quantum number of this hypothetical particle, were it to exist, must be -3. If such a particle existed in nature, then that would be a beautiful pattern, once again, in conformity with group theoretical predictions. The group theoretical symmetry operations we are now talking about is known in mathematics as SU3, for those of you who are interested in such things. Now, so to repeat again, the underlying symmetry of this theory is SU3, whose generators are 3 by 3 matrices, unitary matrices, 3 by 3 matrices, which represent rotation in 3 dimensions. Now, this theory predicted a new particle, which they called as omega minus. The properties of this particle were precisely predictable according to this group theoretical argument. Its strangeness quantum number must be -3, and its mass was also predicted because the mass difference between these different rows were theoretically calculated. So that particle was postulated to exist based upon SU3 symmetry. Now, the strangeness number of this hypothetical particle, as I said, was -3. If you go to YouTube and type in YouTube, strangeness -3 by Richard Feynman, you will see a 15-minute video, a documentary, in which Feynman and Gell-Mann, as well as Neumann, but it is mostly Feynman, talking about this sensational discovery. I very strongly recommend that you see this movie. It's a beautiful movie, and you will see Feynman at work. How beautifully explained with just a piece of chalk paste. Of course, this video is meant for the general public, and so you will really enjoy seeing it. It's called strangeness -3. Now, omega -3 particle was eventually found, and it had the predicted properties. So no sooner was omega minus found, Murray Gell-Mann was awarded the Nobel Prize for Physics in 1969. So the strangeness quantum number that he had discovered and which he had scribbled on the table, which I was fortunate to use for a while as a beginning student at the Fermi Institute, was awarded the Nobel Prize in 1969. Now we will turn to a different subject, the unification of forces. As I said, in today's world, there are 4 distinct forces of nature: the strong force, the electromagnetic force, the weak force, and the gravitational force. They are described by separate theories. The idea is that when the universe was extremely young, extremely dense, extremely hot, and therefore particles had incredibly high energies, all the 4 forces of nature can be described by a single unified theory. Now, this dream hasn't been achieved yet, but it has been partially achieved. 3/4 of the mission has been completed. So I will tell you about this. It is very important for us to understand this because it is one of these grand unified theories, or rather when it breaks down, that gives rise to the exponential expansion of the universe, which is really the topic that we are discussing. This is all preparatory work. The notion of unifying fields goes back to James Clerk Maxwell. Before Maxwell, the electric field and the magnetic field were thought to be unrelated, the works of Ampere, Faraday, and so on. But Maxwell, in 1865, when he formulated his new electrodynamics, electromagnetic theory, he actually unified the electric field and the magnetic field. The electric field and the magnetic field, from then onwards, were no longer separate entities. Soon after general relativity, in 1915, 1916, Einstein and then the great mathematician Hilbert in Göttingen, and then his successor Hermann Weyl, about whom I shall speak presently, tried very hard to construct a unified theory of gravity and electromagnetism. This was Einstein's dream, and he worked on it till his death, but he never succeeded, and nobody else succeeded either. Around 1962, Sheldon Glashow at Harvard University in Boston constructed a unified theory of electromagnetism and weak interactions between the neutron and the proton. A little later, a few years later, Abdus Salam, working at Imperial College in London, and Steven Weinberg, a colleague of Sheldon Glashow at Harvard University, succeeded in constructing what is known as a gauge theory of electro-weak interaction. So they constructed successfully a theory, a unified theory like Maxwell's theory, unifying electromagnetism and weak interactions. So I have to tell you a little bit about the nature of such a unified theory. And that takes us to some pioneering discoveries by Vladimir Fock, a very well-known theoretical physicist in Moscow, and the great mathematician and the great friend of Albert Einstein, Hermann Weyl, who was his colleague in Zurich in Switzerland, and then later on his colleague at the Institute of Advanced Study in Princeton, where Einstein died in 1955. Vladimir Fock was a student of Alexander Friedmann, of the Friedmann universe that we have discussed. Now, we pick up the story in 1954 when Chen-Ning Yang and Mills introduced a new paradigm in elementary particle physics known as gauge symmetry. They constructed what today we would call as a gauge theory. Now, the idea of a gauge theory was not new, was not originally due to Yang or Mills. It dates back to 1925, when Vladimir Fock in Moscow extended the gauge invariance of Maxwell's theory to the Dirac equation, describing the interaction between an electron and the electromagnetic field. In 1928 and 1929, the great mathematician Hermann Weyl formalized the concept of local gauge transformations and formulated the idea of a class of theories which have now come to be known as gauge theories. So now I should explain to you what is a gauge transformation and what is a gauge theory. Now, we won't go into the details of this because it's rather complicated, but I would like you to get a feel for it, because this has been the paradigm of elementary particle physics for the past 75 years and underlies every attempt to unify the four forces of nature. So please bear with me for a while and listen carefully. Let us go back to Maxwell's electrodynamics. Maxwell's equations, as some of you may know, are invariant under the transformation. Let me remind you, I discussed this when we discussed in an earlier lecture electromagnetic radiation accelerated charges. You can describe Maxwell's theory either in terms of the electric field and magnetic field, or in terms of a vector potential A, which is a vector, and a scalar potential phi, which is a scalar. Now, if I replace the vector potential A by A prime, where A prime is equal to A plus the gradient of a scalar chi, and if I replace the scalar potential phi by phi prime, where phi prime is equal to phi minus 1 by c d chi by dt, Maxwell's equations remain unchanged. They remain invariant under this gauge transformation. All right? It's a very mysterious thing why this is known as gauge transformation. The origin of the word apparently is related to different gauges used by railways in different countries. In mountainous countries, you have narrow gauge. In India, when the British set up railways in the 1850s, it was a meter gauge. And then in Europe and in England, it was a broad gauge. So these are different gauges. So in a similar fashion, these are known as gauge transformations. All I want you to know is that if you replace A by A prime, phi by phi prime, Maxwell's equation remains unchanged. That is in classical electrodynamics. Now you have to ask what happens in quantum physics, where Maxwell's theory has to be replaced by Dirac equation for the electron interacting with the electromagnetic field. It was shown by Vladimir Fock and then later on by Hermann Weyl that for quantum dynamics to remain unaltered by such a gauge transformation, A prime is equal to A plus gradient of chi, etc., then the wave function in Dirac equation, for example, the wave function psi must be replaced by psi prime, where psi prime is equal to psi into e to the power I chi. I have dropped out h bar and so on in the exponent there for clarity. So what is this factor e to the power I chi? Chi is the scalar that comes in the gauge transformation. So consider the Dirac equation, for example. What we are saying is that the dynamics of the electron, which is described by Dirac equation, remains unchanged if the wave function is multiplied by e to the power I theta. Now e to the power I theta is cos theta plus I sin theta. That is just a simple rotation by an angle theta, right? So you can imagine the Argand diagram and rotating it by an angle theta. So what we are saying is that if the wave function is rotated by an angle chi, then the solutions of Dirac equation remain unchanged. Another way of stating this is simply that in quantum mechanics, that the phase of the wave function is not observable. What is observable is only the square of the amplitude of the wave function. The phase of the wave function is not observable. Under some special circumstances, like in superconductivity and superfluidity, the phase of the wave function does have observable properties, rather the gradient of the phase of the wave function. But you may not remember our discussion of the interiors of neutron stars, so let's not go back that far. So this is known as gauge invariant. So what I'm saying is that just as Maxwell's equations are invariant under gauge transformation, Dirac equation is invariant under gauge transformation because it merely represents global rotation of the wave function or a simple phase of the wave function which is unobservable. So this is known as gauge invariant. So in electrodynamics, quantum electrodynamics, you're talking about a global rotation, a global symmetry. Theta is a global rotation. Everywhere is same. So the dynamics remain unchanged if the wave function is multiplied by e to the power I theta. This is known as gauge invariant. Now, let's come to the crux of the matter. But suppose I do not make a global rotation e to the power I theta. I make local rotation, and each point x, y, z, I rotate by a different amount. Then the question is are the solutions of Dirac equation invariant under such local gauge transformations? And the answer is no. The dynamics does not remain the same if theta is a function of x. In other words, if I make local rotations. But the gauge invariance can be recovered if I add to this theory a new field, which we shall call as a gauge field. All right? So what I'm doing is, some internal symmetry makes me want to do local rotations, local gauge transformation. But if I do that, then I am disturbing the dynamics of the system. And in order for the dynamics to remain invariant under local gauge transformations, I must introduce a new field, a gauge field. For every gauge transformation, I have to introduce a new field. If there are 3 symmetry operations that I can do, then I have to introduce 3 gauge fields. If there are 5 symmetry operations I can do locally, then I have to introduce 5 new gauge fields. Okay, so that's the name of the game. So these theories are known as gauge theories. So gauge theories have become the paradigm of particle physics since Yang and Mills' paper of 1954. I do not expect you to have understood much of what I said, but all I want you to remember, tomorrow if you are asked, you should be able to say that elementary particle theories since 1950s are what are known as gauge invariant theories. They are invariant under local gauge transformation. So Yang and Mills introduced this paradigm because they were trying to describe the symmetry between neutron and proton due to isotopic spin. They were considering local rotations, which are SU2 rotation, rotating the isotopic spin from up to down, down to up, up to down, at different places. And so that is the theory they tried to construct. The attempt was to construct a theory of strong interaction between neutron and a proton, incorporating the isotopic spin symmetry between the neutron and the proton. Well, this idea was beautiful and promising, but it was immediately shot down, not surprisingly, by Wolfgang Pauli, as I shall explain. Now, the local symmetry operations that we are talking about, local gauge transformations that we are talking about, may not be symmetry operations in physical space, the space in which we live in, the space in which the neutrons, protons live in. They could be internal spaces. For example, the spin angular momentum is an internal symmetry of the particle. The isotopic spin is an internal symmetry between neutron and a proton. Therefore, when we are talking about local symmetry transformations, local gauge transformations, these need not be transformations in physical space. They could be, like in electrodynamics, there could also be symmetry operations in internal spaces. They need not be global rotations. They could be local rotations represented by 2x2 matrices, such as these Pauli matrices. They could be 3-dimensional rotations represented by unitary 3x3 matrices, which is the group of SU3. We won't go into these details here. Now, here is the punchline. Since Yang and Mills of 1954, it has been believed now that all interactions of nature between elementary particles, all fundamental interactions of nature, are described by gauge fields. What are these gauge fields? These are fields that are introduced so that the dynamics remains invariant under local gauge transformation. I shall explain this presently, and it will become clear. For every symmetry operation, a new vector field, a gauge field, is introduced. So if I do a local rotation, SU2 rotation, then I introduce a gauge field. If there are many symmetry operations, I introduce many gauge field. Now, one of the paradigms of quantum field theory is that quantum fields are, in quantum mechanics, fields are described by quantum fields. Elementary particles are regarded as excitations of these quantum fields. The photon is an excitation of the quantized electromagnetic field, and so on. So similarly, the excitations of these quantized gauge fields are particles, and these particles obey Bose-Einstein statistics, and therefore the excitations of the gauge fields are known as gauge bosons. So we are really talking about particles are not fields. Particles are excitations of fields, just as photons are excitations of fields. Phonons are excitation of the quantized lattice vibration field, and so on. So similarly, the excitations of the gauge field are known as gauge bosons. If there are 5 gauge fields, then the theory has 5 gauge bosons. If there are 8 gauge fields, then the theory will have 8 gauge bosons, and so on. Now, here is the punchline. Interaction between elementary particles is believed to be mediated by these gauge bosons, just as the electromagnetic interaction between charged particles, electron, proton, and a proton, is mediated by a photon. A photon is a gauge boson. Okay? The gauge field is the electromagnetic field. Excitations of the electromagnetic field are photons. So the electromagnetic interaction is mediated by exchange of gauge bosons, in this case gauge photon. In general, any interaction between elementary particles, strong interaction, weak interaction, and so on, are mediated by the exchange of these gauge bosons, which are excitations of the quantized gauge fields. So, to repeat once again, in quantum field theory, elementary particles, all elementary particles, are excitations of the fields. Photon is an excitation of the quantized electromagnetic field. Excitations of the gauge fields are known as gauge bosons. These are massless particles which obey Bose-Einstein statistics. Now, the Salam-Weinberg-Glashow unified electroweak theory is such a gauge theory. Now, what is the gauge symmetry of the theory? What are the local transformations? The local transformations belong to the group SU2 cross U1. It's a larger symmetry than SU2, which is rotating, two-dimensional rotation about a third axis, given by the Pauli matrices. And U1 is a global rotation, e to the power I chi is a global rotation. So this SU2 cross S1, U1, is the symmetry transformation of the Salam-Weinberg-Glashow electroweak theory. Now this theory has 4 gauge bosons because there are 4 gauge fields corresponding to the following particles: W plus, W minus, Z0. These are 3 massive particles. 2 of them are charged, 1 of them is neutral, and the 4th gauge boson is the photon, which is responsible for the electromagnetic interaction. So let's try to sink in this idea. So here is the familiar quantum electrodynamics. The interaction between charged particles is mediated by a virtual photon, which is the gauge boson. Now, if you unify electromagnetism and weak interaction, there's a new gauge boson, which is known as the Z0 gauge boson, a very massive particle, electrically neutral, and that is known as neutral current interaction. So two charged particles can not only interact by exchanging a virtual photon, which was quantum electrodynamics, but also by exchanging a neutral particle Z0, which is not there in quantum electrodynamics, but which is there in the unified electroweak theory. In addition to Z0 and the photon, there are two other particles, W plus and W minus, which mediate the interaction between charged particles. So electroweak theory unifies electromagnetism and weak interaction, and the forces are mediated by four Bose-Einstein particles: the photon, the Z0 particle, W plus particle, and W minus particle, which are postulated by the gauge theory of unified forces of Salam, Weinberg, and Glashow. Now, their idea was that if you are at an energy about 250 GeV, which corresponds to temperature in excess of 10 to the power 15 Kelvin, a single force describes electricity, magnetism, and weak interactions. That is the electroweak theory. Now, this electroweak theory predicted the masses of the Z0 particle, W boson plus and W boson minus. And these particles were found eventually in 1983, and they had precisely the properties that were predicted by Salam, Weinberg, Glashow theory. Even before these particles were discovered, so let's summarize. In electroweak theory, there are four gauge bosons, W plus, W minus, and Z0, and the photon, of course. These gauge bosons mediate the electromagnetic weak interactions. These gauge bosons are massless particles, but the W boson and the Z boson acquire mass when this symmetry is spontaneously broken. More about that in a moment. Just accept the statement. And this is, of course, the famous Higgs mechanism. Now, I have to explain what I mean by a massless particle acquiring mass. And this is very important. When the universe was very young, there was just energy. There were all kinds of fields, quantum fields, but there were no massive particles. The excitations of these fields were bosons, but they were massless bosons. But the world in which we live in, except for particles like photon, neutrino, and so on, particles are masses. How did they acquire mass? A little digression is needed here. Here I'm talking about some of the most beautiful and most profound physics of the last 50 years. Much of it derived inspiration from the theory of superconductivity. Let me explain. In 1937, Lev Landau in Moscow formulated his famous theory of second-order phase transition. Landau introduced the concept of an order parameter, a parameter which is zero in the high temperature phase, but which is non-zero in the low temperature phase. Okay? I'll explain that. The low temperature phase has a new property. It has a long range order. Again, I will explain this with examples. Please bear with me for half a minute. What do I mean by long range order? Take a crystal. If you take liquid, for example, in a liquid, the atoms and molecules can be anywhere they like. There is complete translational symmetry. There is Galilean invariance. But in a crystal lattice, if I know the position of one atom, then I know the position of every atom in an infinite crystal lattice. So there is a long-range translational symmetry. All right? Okay. It is there in the solid phase, but it is not there in the liquid phase. I'll give you more examples in a minute. In a ferromagnet, the orientation of spin has long-range order. Above the Curie temperature, iron is paramagnetic, copper is paramagnetic. That means the spins individual spin angular momenta can point in any direction they like. So there is orientational symmetry. Okay, a rotational symmetry is there. Spins can point in any direction they like. But in a ferromagnet, below the Curie temperature, all the spins point in the same direction. It could be that direction, it could be that direction, it could be that direction, doesn't matter. But they point in the same direction. So there is long-range order in the orientation of the spins. So I'm giving you an example of what Landau meant by an order parameter. The spontaneous magnetization in a ferromagnet is an order parameter. So a paramagnet does not have a net magnetization. The net magnetization is zero. But a ferromagnet has a net non-zero magnetization. So that is a long-range order. That is the order parameter. Now what I have plotted here on the y-axis is the free energy, and what I have plotted on the x-axis is the order parameter, m. Now what Landau said was, in his very, very celebrated theory of second-order phase transition, is that the free energy can be expanded in powers of the order parameter. F of t is some f0 of t minus tc m squared plus beta m to the power 4. Now, when you are above the transition temperature, when alpha is greater than 0, beta is greater than 0, then above the critical temperature, the free energy has a minimum where the order parameter has a value 0. At the critical temperature, the free energy becomes very flat. Just below the critical temperature, the free energy has a double minimum and a maximum at the center. So, at high temperature, the free energy has a minimum, a global minimum over there. At low temperature, the free energy has a global minimum at that value of the order parameter or at that value of the order parameter. All right? So let me show this once again. I've given a three-dimensional version of it. So when temperature is above a critical temperature, the free energy has a minimum at phi equal to 0, where the cursor is pointing. The free energy has a 0 minimum, phi, the order parameter, or m, whatever you choose to call it, has a value 0. There is no long-range order. But below, at the critical temperature, a new global minimum appears at a finite value of phi, or m, which is over there. Now you notice that the minimum is actually has a circular symmetry. So it's like a saucer. If I put a billiard ball in the saucer, it can be anywhere in the saucer with equal amount of free energy. It doesn't cost energy to move the ball bearing or the billiard ball around the saucer. Or in this Mexican hat, the system can be either there or somewhere over there. What this means is the following. So in the representation over here, I have taken phi as a complex variable, a real part along the x-axis, and an imaginary part along the y-axis. So that is like an organ diagram. So there is a polar vector rotated by an angle theta. Therefore, when the system undergoes a phase transition from a paramagnet to a ferromagnet, the system jumps from a global minimum over there to this global minimum. And the symmetry is broken. What is the symmetry that is broken? The rotational symmetry of the spins is broken. So let's try to understand this concept of spontaneous symmetry breaking. The system jumps from there, which is a local maximum over there, to the global minimum over there. Now the spontaneous magnetization vector, as I said, can point anywhere in space. There, which corresponds to the system being anywhere in this azimuth direction. So one would say that although the Hamiltonian of a ferromagnet, which is given by SI dot Sj, where SI is one spin and Sj is a neighboring spin, whereas SI dot Sj is invariant under global rotation, the ground state of the ferromagnet breaks the symmetry. The spins are aligned either in that direction or in that direction or that direction. They are aligned. There is long-range order. All right? So that is the concept of spontaneous symmetry breaking. Most phase transitions are associated with symmetry breaking. So let us understand this with a few examples. The high temperature phase is always the more symmetric phase, and the low temperature phase is the less symmetric phase. All right? Now the symmetry that is broken or the symmetry that is lost when there is a phase transition may be either a continuous symmetry, like a rotation symmetry, or maybe a discrete symmetry. In the case of a paramagnetic to a ferromagnetic transition, the symmetry that is broken is the rotational symmetry. Whereas when a liquid becomes a solid, the symmetry that is broken is the translational symmetry, which is a discrete symmetry. The atoms in a solid can be either there or there or there, not nowhere in between. All right? So it can be either a continuous symmetry that is broken or a discrete symmetry that is broken. Breaking of a continuous symmetry is usually associated with second-order phase transition, and breaking of discrete symmetry is often associated with first-order phase transition. Now, the absence of symmetry in the low-temperature phase has profound consequences. This is what I'm coming to now, so listen carefully. Let us consider the paramagnet to ferromagnetic phase transition. So this is a paramagnet. The spins in a paramagnet can point in any direction they like. There is rotational symmetry. But in a ferromagnet, they all point in a different, same direction. The direction itself can be arbitrary, but they all point in the same direction. In an anti-ferromagnet, they point up and down, and so on. Then there is a ferrimagnet, and so on. These are variants. The important thing to appreciate is that in all cases, the paramagnetic phase, the high temperature phase, the phase about the Curie temperature is the more symmetric phase. And the less symmetric phase is the low temperature phase, the ferromagnet or the antiferromagnet or the ferrimagnet. And the rotational symmetry is either broken or lost, whichever is the phrase that you prefer. Now, what I want to emphasize here is that when a rotational symmetry is broken in a phase transition, a new property emerges. What is the new property in a ferromagnet? It is called as a spin wave. So here is an example of a spin wave on a chain. This is just a one-dimensional magnet. If spins are all aligned, then you can perturb one spin, take a bunch of matchsticks and tie them to a string and hold it stiff. If I take one matchstick and move it and let go, and then you will see a wave propagating in the spin, in the string. So this is the concept of a spin wave on a chain. So the spin wave in a magnet, which is well observed by neutron scattering experiments, is an emergent property due to the symmetry breaking. Now, in the case of liquid-solid phase transition, the symmetry that is broken is translational symmetry, and the emergent property is rigidity. You can't stand on a liquid, but if the liquid freezes, you can stand on it. A solid has rigidity, and the rigidity is a consequence of the broken symmetry. Now, in the case of superconductivity, the symmetry that is broken is the gauge symmetry of Maxwell's theory. And the emergent property is the supercurrent and diamagnetism, also known as Meissner effect, which expels magnetic field from a superconductor. Therefore, spontaneous symmetry breaking results in emergent properties, which are extremely important for macroscopic behavior. The emergent properties examples are rigidity of solids, superconductivity, spin waves, etc. Now, let us go to the world of elementary particles, which is our story today. What has all this got to do with the price of fish? As soon as the theory of superconductivity was constructed in 1957 at the University of Illinois, not far from Chicago, by Bardeen, Cooper, and Schrieffer, Robert Schrieffer, one of the students involved in that, came to Chicago and gave a seminar. Attending that seminar was a great Japanese theoretical physicist at the University of Chicago. Many years later, one of my teachers at the University of Chicago, Yoichiro Nambu, a very profound physicist, immediately pointed out that the superconducting ground state of Bardeen-Cooper-Schrieffer theory violated gauge invariance of Maxwell's theory. This had not been appreciated by the discoverers of the theory. So Nambu was the first to realize that the superconducting ground state lacked the gauge symmetry of the Hamiltonian. Although the Hamiltonian of BCS theory is still invariant under gauge transformation, the ground state, which is the superconducting state, is not invariant under gauge transformation. Now, he pointed out that the spontaneous symmetry breaking had a profound consequence for the condensate, which is the superconducting ground state. For example, the photon in a superconductor acquires a finite mass. And this mass is related to the finite London penetration depth. In other words, the electromagnetic field does not penetrate except for a thin layer into the superconductor. That is why the superconductor is a perfect diamagnet. Anyway, the important thing is that Yoichiro Nambu then borrowed this concept of spontaneous symmetry breaking and its profound consequence for the condensate from condensed matter physics to elementary particle physics. And he constructed a quantum field theory based on this idea of spontaneous symmetry breaking. Now, this idea of Nambu of 1960 was picked up and formulated in a field theoretical language by Geoffrey Goldstone, who was working on the other side of the Atlantic in Cambridge University in England. Geoffrey Goldstone in 1962 proved a rather fundamental theorem, according to which if a continuous global symmetry is broken, like in a ferromagnet, then there must appear a massless scalar boson. A massless scalar boson must appear in the theory, and that massless scalar boson is known in the literature as the Nambu-Goldstone boson. Example of such a Goldstone boson is the spin wave in a ferromagnet in the non-relativistic example. In quantum electrodynamics, such a gauge boson, massless scalar boson, is the photon. And now we come to the crux of the whole story, the punchline of the story. And that dates back to 1964, when Robert Brout and Angler in Belgium and Peter Higgs in Glasgow in Scotland independently made the major breakthrough. In the case of local gauge symmetry, for example, local rotations, the massless scalar boson appears in the theory. That is the theorem due to Geoffrey Goldstone. Now, in 1954, Yang and Mills had hoped that this boson will mediate the force between the neutron and the proton. They constructed this gauge theory of elementary particles. But Pauli quickly shot it down. He said this cannot be true, because he said if the force between a neutron and a neutron and a proton is mediated by a massless boson, then the nuclear force has to be infinitely range, like the electromagnetic force. But the nuclear force is extremely short range, only of the order of 10 to the power minus 13 centimeter. Therefore, whatever is mediating must be a massive particle, like Yukawa had conjectured. So it couldn't be this massless scalar boson, and therefore this theory of Yang and Mills, whereas it proved very attractive, was suddenly stuck. There was a stumbling block. Now this problem was finally broken in 1964 by Brout and Angler and Higgs, quite independently, where they showed, based on analogy with superconductor, which had been elucidated earlier by Nambu and then later by Phil Anderson, a very well-known condensed matter physicist, that the massless scalar boson, the Goldstone boson, the Nambu-Goldstone boson, which is now called the Higgs boson, would acquire a mass when the gauge symmetry is spontaneously broken. Just as the photon acquired a mass in a superconductor because gauge symmetry was broken, when the local gauge symmetry was broken, Brout and Angler and Higgs argued that the massless boson will acquire a mass. That is the Higgs mechanism. So the Higgs field, which was a massless boson, became a massive boson. And all the other massless fields, the fermions and the leptons, the quarks and the leptons, the electrons, the muon, the tau meson, they were all massless particles. They interacted with the Higgs particle, which now had a mass, and they all acquired a mass. So this is the paradigm of particle physics. So the idea is that the electroweak gauge boson, W plus W minus and Z naught particle, acquired a mass when the SU2 cross U1 symmetry was spontaneously broken, and these bosons were found in 1983, and their masses were precisely predicted. But long before this verification, Glashow, Salam, and Weinberg were awarded the Nobel Prize for Physics in 1979 for successfully constructing a gauge theory of electroweak interaction. A lot of people were very unhappy when this Nobel Prize was given because there was no experimental proof for the existence of the neutral current Z0 particle and W plus and W minus, let alone having the masses that were predicted. Fortunately, all was right. The mass of the W bosons and the Z bosons were eventually measured. The mass of the W boson was 80 GeV, and the mass of the Z boson was 91 GeV, both roughly 100 GeV. In other words, above an energy of 250 GeV or temperature greater than 10 to the power 15 Kelvin, a single force describes both electromagnetism and weak interactions. And as soon as the masses of W boson and the Z boson were measured, Carlo Rubbia and van der Meer at this giant collider in Geneva in Switzerland, where this discovery was made, were awarded the Nobel Prize for their decisive contribution to the Large Hadron Project, which led to the discovery of the field particles W and Z, which are the communicators of weak interaction. Now, these particles have an energy of only 80 GeV or so. But the Higgs boson, which was christened the God particle, and there is Mr. Higgs standing near this detector in Geneva. This detector had to be built to go to much higher energy so that the Higgs boson creation could be observed experimentally. And it took 30 years for the Large Hadron Collider to reach the energy that was needed to materialize the Higgs boson. The Higgs boson was eventually found in the year 2012, and its mass was exactly what was predicted, 125 GeV. All right? And so the very next year, François Englert and Peter Higgs were awarded the Nobel Prize for Physics for this very profound discovery. Sadly, Robert Brout, whom I personally knew, passed away between that period, so he could not be awarded a Nobel Prize posthumously. Right? So Englert and Higgs were awarded the Nobel Prize for the discovery of the Higgs boson. So the paradigm that all elementary particles owe their masses to interaction between them and the Higgs particle, and that the Higgs particle itself acquires mass when the spontaneous gauge symmetry is spontaneously broken, and the massless Higgs boson acquires a mass. So this is the paradigm of particle physics now. So the grand unified field theory, which is the standard model of elementary particle, is now a unified theory of strong forces, weak forces, and the electromagnetic forces. The gauge theory, the symmetry of SU3 cross SU2 cross U1, this is the symmetry of strong interaction, this is the symmetry of weak interaction, this is the symmetry of electromagnetic interaction. And there are 5 gauge bosons, or more precisely 8 gauge bosons: photon, Z0, W plus, W minus, and the gluons. So here is the standard model of the elementary particles. You have the quarks, up quarks, charm quark, top quark, down quark, strange quark, bottom quarks. Then you have the leptons, the electron, the muon, the tauons, and the three neutrinos associated with these three leptons. And then you have the four gauge bosons, the gluons which bind the quarks together, the photons which bind charges together, and the Z boson and the W boson which bind the weakly interacting particles together. And then presiding over all of them is the Higgs particle, the Higgs boson. So, the photons mediate the electromagnetic forces between charged particles. The W plus, W minus, and Z0 mediate weak interaction between the leptons and quarks. The leptons and quarks interact by weak interaction, and that is mediated by these three gauge bosons. The gluons mediate the strong interaction between the quarks. They bind the quarks together to form the neutron and the proton. The grand unification is achieved above an energy of 10 to the power 25 electron volt, or a temperature greater than 10 to the power 29 Kelvin. Such high temperatures were obtained when the age of the universe was less than 10 to the power minus 35 seconds. But gravity still remained a separate force even at that time, which is known as the Planck era. So that is the grand unified theory. When the universe was only 10 to the power minus 35 seconds old, the strong force, the weak force, and the electromagnetic force were unified into a single force, which is described by the standard model of elementary particles, which we have today. And then at a much lower temperature, the grand unified theory is spontaneously, symmetry is broken, and strong interaction splits from electromagnetism and weak interaction. And that is the grand unified field theory phase transition that Alan Guth was talking about, which we shall discuss in the next lecture. So in the next lecture, we shall return to our story of the inflationary universe. But it was extremely important for me to give you a flavor for the world of elementary particles and the world of unified forces, the paradigm of gauge symmetry and gauge fields, and the concept of spontaneous symmetry breaking and the resultant emergent phenomena, because all of these are precursors to understanding how particles acquire the masses they have. They acquire their masses through what is known as the Brout-Englert-Higgs mechanism, which derives from the deep insight that Nambu had in 1960 about broken gauge invariance in the superconducting ground state. It was very important for me to give you at least some flavor for it. You will find references where you can read this in some more leisurely in the description of this particular video. In the next lecture, we shall go to part 2 of the big and the small and discuss how this microcosm and the phase transitions in the microcosm ultimately influence the universe at large today. Till then, thank you very much for your kind attention, and I apologize for going on for very long, but I did want to finish this story at some level in today's lecture. Thank you very much.